Just a second. Okay. All right. Okay, so this is where we last time. We're talking about desirable features in a language, and we started with simplicity. And just to recap a little bit, simplicity refers to the language. When we say that a language satisfies this, if it has if it has a small feature set, and the rules on how to use them, apply them, and combine them is clear and concise. And then, as an example, we use C as a language that was fairly simple, and Java as a language that was very complex. Now, the next one, orthogonality, is actually very related to simplicity, because especially the parts about the rules and how the way the operators can be combined those rules are very simple. So orthogonality refers to the way in which different constructs, whether it's operators or expressions or values, how they can be combined in single constructs, and whether or not when you do this, it is intuitive and it's meaningful in the language. When we say meaningful, it is that the expression that you get is a valid expression. It compiles, it's allowed. What does that mean? Basically, another way to say this is that the language has as little exceptions as possible. A language that is not orthogonal is going to have a lot of exceptions, a lot of special cases. The language, it doesn't have to be simple in the sense of having a small feature set to be orthogonal, but obviously the more features you have, the harder it is going to be to reach orthogonality. So an example of this would be the following. On how orthogonality is broken. In Java, for example, you have the addition operator. Right now, as a person who is familiar with arithmetic, then you are used to what we call in languages mixed mode expressions. But basically, you're used to expressions in which you use mixed numbers, mixed in terms of what type of sets they belong to, because in number theory and in calculus in particular, we group numbers in hierarchies that are subsumptions of others. So we start with the naturals, then integers, then reals, then rationals. Then rationals, then reals, and then of course we have the irrationals here on the other side. But when you are working with numbers on paper, if you have 1.3 and you have 5, you add them together, and you know it's going to be 6.3. So when you go to a programming language, you would expect that if you have the addition operator available and you can express 1.3 and 5, you would expect that adding 5 and 1.3, it would have to work. That's your intuition. And yet when you arrive to a language like Java, you may find out that it might not work depending on the context. Can somebody tell me what would be a situation in which adding 5 and 1.3 would give you an error in Java?
When you're storing it into an int value, but you need it to be like a double or float.
Can you type that expression in the chat? I'm sorry, who talked? There you go. So, no, that's not the example that I gave, but no, in the example that I gave, one of the numbers was an integer, the other one was a floating point. So let's try that again. Matt?
Okay, so just retype it, but have one of the number as a
Sure.
floating point. Okay.
Okay, there you go. So that Matt says that would not compile. Is that true? Do we all agree on that? Kayla, what do you think? Does that compile? Matt says it doesn't.
It could, but it might just leave off the decimal.
No, it either compiles or it doesn't. So
Okay.
so we have a very specific example here. So I'm asking you, does it compile, yes or no?
No,
Why not?
because the floating point number is too big to go into an int.
Because a floating point number is too big to go into an int. I don't know what that means. What do you mean by big? I mean, 8.4 is not that big.
Oh, okay.
But I see what you're saying. No, it's because Tommy here in the chat is pointing out to it's because the integer, the target here where we're going to store it is an integer. So the only way to be able to store that into the bucket where the where int can be saved, you would have to convert it to an integer. So you have to drop the 0.4, and that would be a loss of precision, like Tommy points out here. And so Java would disallow this, even though we would expect that anytime we would add those two, it should just work. But Java says, no, there's a loss of precision here. And so basically, you would have to force the issue by explicitly casting 3.4 to 3, and then the operation will succeed. Or you would have to, what's the other option? So one option is to cast 3.4 to an int. What's the other option?
Cast the result.
Change int to double. So basically, we change the type of number to float or double. Well, it had to be double because 3.4 here is a double. If we change it to double, then it would work. How do I know that 3.4 is a double?
Because that's what Java will, by default, specify just floating point values that are typed out.
Okay. Why is it not a float? As you know, double or double precision numbers that use 64 bits. Floats use 32 bits. Why is it not a float? Anybody? No? Okay. To be a float, you would have to add an F at the end of the number. We know this, right? Maybe you forgot. So it would have to be, it would have to look like this. And then it would be a float. That's how I know that 2.4 is a double. All right. We good? Yes? No?
Yeah.
I
Yeah,
need some
we're good.
acknowledgement.
Yeah, we're good.
Makes sense.
Okay, I need some acknowledgement. Okay. Right. So in Java, which is weird. I always thought the default should be a single precision. But anyways, but if you just specify like that, then it's a double. Otherwise, for it to officially be a float, either you have to put that F there. Anyways. And so that's one exception. In exceptions like that one, there's a lot of them. And when you are programming, you get used to them little by little. You cannot do this when you do that. You cannot do this when you do that. And that's even though you would expect or you intuitively try to do it, it doesn't let you. The more complex the language, the more of those exceptions to the rule is going to have. And that's going to break this property of orthogonality. If the language is very simple, then it allows you to do all this. For example, in a lot of dynamic languages like Python and Ruby, even though numbers have an underlying representation in terms of their size, so there's integers and there's longs and there's the equivalent to float and the equivalent to double. The languages don't care about that. They just, because there's no, as you know, there's no explicit typing and the type system is dynamic. And so whenever it's given an expression with mixed numbers like that, it just adds them, turns it into a real number, and then stores it, no problem. So you don't have these kinds of issues in those languages. Those languages actually, especially Ruby, they work really hard towards making the language as orthogonal as possible. So you can create all sorts of almost everything you put together, it works in some way, and sometimes not as intuitive, sometimes a lot. So,
Professor?
For example, in Ruby, you can use negative indices for arrays. Yes.
Okay, I hope I don't come off as rude, but you always sound like a bit annoyed. I was wondering, is that how you normally talk, or are you just tired or anything like that? Or
who's that? Who's talking?
This is Benjamin.
I sound annoyed.
Yeah. Is that just your normal speaking voice?
My voice. You mean my tone?
Yeah, your tone.
Yeah, this is how I talk.
Okay, I'm sorry.
Sometimes I am annoyed though. So
Okay.
It's up to you to detect my annoyance or when I'm annoyed. What was I saying? Oh, so orthogonality. And so that's basically what it means. All right. And so if we look at a language, and that language basically has a lot of exceptions like that, or it has a lot of instances in which it would be intuitive for a person to try to build an expression in that way, but it doesn't work. The problem with a language like that in which that is not as orthogonal as we would expect is that it takes longer to learn, because not only do you have to learn all of the rules, all of the different operations, but you also have to learn all of the different exceptions, all of those different little quirks, like you learn early on when you are starting to program in Java, that when you combine numbers, you have to take, there are cases when it's not going to work. And not only that, but in those cases, you also have to be aware of how the numbers are represented to understand the reason, which breaks a little bit it defeats the purpose of using a high-level language, because the idea is that you don't have to worry about the underlying machinery and representation. But in that case, you have to, because it's the only way to understand why this expression is not working. What is it that I need to do to make it work? Again, as the language becomes more complex, then the likelihood of it being orthogonal decreases. And so that means that these two, simplicity and orthogonality, they sort of work in tandem with each other. If the language is simple, it's easier to make it orthogonal. If it's complex, then it's not. Any questions?
So far, so good.
So far, so good. Okay, the next one is level of abstraction. So level of abstraction is basically how good is the language at providing constructs or features that allow me to build complex abstractions. Let me ask you then, what is an abstraction? What does that mean? Because I can basically sit here and talk about data abstraction, but what does that mean?
It's kind of like a model an abstract model that you can base other code off of, so you can kind of like reuse the model, reuse code.
Well, it has nothing to do with necessarily, that is, with reuse, but a lot with what you said first. It's a model, right? So an abstraction in code is some sort of arrangement of different constructs and features that represent something. The more powerful the abstraction, then the more it requires me to understand intricate details of the code to see what it maps to. Because the idea of an abstraction in code is that it maps to some sort of entity in the problem domain that you're trying to solve. For example, if you are making or writing a program to control a set of drones, then you would expect to find in the code some sort of data abstraction that represents drones. If you're programming it in C, then there are facilities there to do it, but the way it would be very rough. And because you basically have to, the best way to do this in C would be to use a bunch of structures. I don't know if you're familiar with C, which are very, very basic data abstraction facilities in C. And they would not map, the mapping would not be as neat. It would just look like a bunch of code with a name that somehow is representing the drone. However, if you do it in Java, we have classes and we have interfaces and we have abstract classes. And the classes, the way they're designed, they're allowed to for us to represent behavior in the form of methods and state in the form of fields. And so now when you look at a class, you can see how it maps directly to the entity in this case. And so obviously, well, I guess what I'm trying to say is Java has very powerful data abstraction features, whereas C basically doesn't have any, except for structures and unions. which is a very, very, very rough structure. It's basically a record that has a bunch of variables in it that you can assign values to and name, and that's it. There's no information hiding. There's none of the other really powerful abstraction features that we have in Java. Obviously, the more for a language to provide a high level of abstraction, it needs to be complex. And so that means that these two, simplicity and level of abstraction, they are going to be in tension with each other. You basically cannot have you cannot have one and the other at the same time. Either the language is simple, or it is complex enough to provide, all of the facilities that you need to create strong, powerful abstractions in your code. Does that make sense?
Wait, so these bullet points are not like a tier list. They're just points. They have equal value, basically.
That's why it's not a number list.
Okay, I just want to make sure.
Yeah. There's no, how do I put it? They're all, it says up there, desirable features. They're all desirable to the same extent. The point is that you can't have them all. And so this is why, there's no one language to rule them all, like I said at the beginning, because you can't have a language that has all of them. And that's why there's languages for different applications. So let me give you an example. Suppose you're trying to, another example, I guess. Suppose you're trying to program a business application. So in a business application, powerful abstractions are very important. But typically, you're dealing with, depending on the business, but you're going to be dealing with databases. You're going to be dealing with records of personnel, accounts, stuff like that. And in that case, you want a very high level language, right? That you can map directly to the business problem at hand. Makes it easier to program. The issue with languages that provide a high level of abstraction is that they're not only complex in the design of the language itself, but they have to be complex also in their implementation. So, for example, again, I go back to Java, but it could also be C#, which is also a language that's very popular in business applications. Because they have so many different features that are very high level and it cannot be mapped directly, I guess is one way to put it, to the instruction set of the computer. Then they need a lot of runtime support. You might not know this, but when you run a Java program, it's not like when you actually, when you run a C program, there's also some runtime support, but not as much. You're not just running the code, but the VM that's running the code, it's not just interpreting the code, but there's these other, let's call it side modules or programs that are running along with it that are doing a lot of the work that was not even in the code. For example, when you run a program in Java, there's another program running called the garbage collector that's keeping your memory clean. You don't need that in C. I mean, you don't have that in C. But the problem in C is that you have to do memory management on your own. So whenever you allocate something, you have to remember to deallocate it, or you're going to have a memory leak. But in Java, you have that. You have the memory manager. You also have the security manager running, all right, to make sure that the resources used by the program are in accordance to the business policy and the security policy of the virtual machine. And so on and so forth. You have a lot of other excuse me, runtime runtime support. running in what a Java program. So what that means is that the system it runs in, it has to be powerful. It has to be a server with a powerful processor and tons of memory. Suppose then now that you are, instead of that example, you are programming, you're writing a program for a embedded controller, the embedded controller excuse me, for a dot point matrix. I don't know if you know what a dot point matrix is, but basically it's like a very complex display in which you control what's shown by controlling the illumination of different dots independently. Well, and typically, you know, you use like a little controller, a small controller, just to program that. Well, using a language like Java that's so complex and requires so much would not only be an overkill, but it will also be almost impossible. Because in this case, the footprint of the program has to be small. In other words, there's very limited memory, and there's this very limited processor power. So in that case, you want to use a language that is very simple. Oftentimes, as simple as programming directly in whatever instruction set that particular chip has, but not necessarily. You can use something like C or a special version of C that has been reduced even more, or a special version of a language like Java that also has been simplified, like eliminated a lot of the features of a language with a much more simpler and where the code is actually compiled into the instruction set. And so you can see how you have two different applications, and the needs for both the language and how they're implemented are going to change. All right. And so for the one that is super complex, you want high level of abstraction. For the one for the controller, you don't care so much of abstraction as you care for simplicity. Because in the controller, you're going to be all you're going to care is for somehow representing the dot matrix and the illumination in each, and whatever algorithm you're going to be doing and how you're going to process the incoming data. And that's it. And that's fine for you because of your constraints. Does that make any sense? I've been talking for like 5 minutes straight.
No, that makes sense.
Any questions? All right, so yeah, okay, good. So basically that's what, so simplicity and level of abstraction are in tension with each other. Typically a language is either simple or it has a high level of abstraction. You can't have both. You can, of course, strike a middle compromise where it's not necessarily simple, but it's not as complex. And of course, abstraction features are not as powerful, but there's still some in there. Something else that you want in a language is portability. So portability refers to the degree to which the program can be moved. Now, when we say move, it doesn't mean necessarily like you can take it from a computer to another, but it could be from a system to another. For example, suppose there's a mainframe and it's running a particular operating system. It has all of these programs running in it. And then for some reason, at some point, let's say there's a business reason where the company loses or the license for that particular operating system expires and they don't want to relicense that. They want to buy another one because it's cheaper. And now you have to install a new system, but now you have also all of this code that you've written for that machine on that system. So what you would want is that, because the code and the operating system, they're two different things. What you would want is that you can take all of your code, save it, and then install the new system and find a way to take your code and port it to the new system. Find a way to make it run there. The degree to which the language helps you do that is extremely important because it saves you a lot of money, potentially having to rewrite all of that code for the new system. I don't know if you know this, but let me ask you this: what would be a instead? What do you think would be a good example of a portable language, as far as you know?
Wait, hold on. Sorry. Why don't you just this may sound ignorant, but why don't you just move everything to GitHub and then re-download it or to another computer or something like that?
Oh, yeah, that's what we want. When I say save it, is you put it on something like a repository and then you bring it to the new computer. Yes. What would that be? Well, it's not the new computer, it's the same computer. Right? So the issue is not that we change computers. In the example that I was given, the issue was we have the same mainframe, the same servers and all that, but we changed operating system. Let's say we migrated from Windows to Linux or from Windows to something else. And so now I'm taking the code that was running before on there and I'm going to move it to the new system. That's the issue here.
Okay.
And so I don't know if you know this, but that's not a trivial thing. Before I continue on why it's not, what would you, as far as you know, what do you think is a good example of a portable language?
I think most modern languages are portable, like C++, Java, Python, I think, as well.
Okay. Why is Java portable?
JVM, the Java virtual machine, which we run on. So all the code is like I forgot what it was called, but basically it turns into like a certain version, which can be used for any JVM. And then since it's a virtual machine, it doesn't matter which OS you're running on.
So in the example that I just gave, all I would need is to have an implementation of the VM for the new system. And if it's available, then not only can I move the code, I can move the binaries. So that's another level. Because if it's only the code, I would have to recompile it. And that's fine, but compiling big bases, I mean, you guys, probably the programs that you're used to, you compile in seconds. But a big code base could take days, hours, sometimes days to compile a full, code base. So that's a lot of work. In the case of Java, though, like you mentioned, because it's compiled into bytecode, if I have an implementation of the VM in the new system, I can just move the binaries and with some minor work, it should just start working right away. But you also mentioned C++. How is C++ portable?
I mean, so far my experience with C++ is very primitive. So I guess it's just work on any operating system. As far as I know.
I'm sorry, you said your experience is very
so yeah, so far like my experience is like C++ is kind of like a primitive like programming language. So it's kind of
you say primitive?
Yeah, I mean
you mean like old or
oh no, it's like I don't know. It was like it's communicate with the computer on like a very like primitive level. Like they not like not like working on the hardware, but then it's just very primitive. It's not like require a lot because it's so simple, like we discussed last time.
No, I said when I talk about simplicity, I talk about C, not C++.
Oh,
C++
okay.
actually is maybe you thought I was talking about C, but you said C. Well, whoever talked, I don't know if it's the same person, but somebody mentioned C++, Java, Python, and that I was asking to that person why they think C++ is portable. If it's you,
Yeah, that was me.
okay.
I said C++ because from what I remember, C++ can be run on most, what was it? Most operating systems. There's like a, yeah, that's about it.
Okay, but just because it can be used in multiple systems doesn't mean you can move code. Those are two different things, right? When when you use C++ in say an Apple computer and you compile it, it compiles to whatever code, whatever instructions said the whatever chip the Apple computers. I don't know what they use nowadays because they moved. I think they're using Intel right now, right? Is that right? I forget. I think most Apple computers nowadays use Intel chips. Anyways, the point is, it's gonna compile to something. You use it in another system, it compiles to something else. Those binaries are not compatible. You cannot move the program from one to the other, just like that. So what you can do in Java, you cannot do it in C++. You cannot move binaries between systems. You can move the code, but even in especially in C++, that is not a trivial matter, because as it turns out, C++ is a language that has evolved differently in different systems. So sometimes you have code that was written, say, for Windows platform, and you move it to, say, an Unix system, and try to compile it using the compiler, the C++ compiler for the system, and it just won't compile because it's using non-standard features that are proper to the other system. And so that's a problem. So usually what you do with C++ is, if you care about portability, you have to refer to some, so there's like the POSIX standard. There's several standards that you can use where it restricts the features that you use to only those that you know that are going to move from one to the other. So everything that I've said can clearly tell you that C++ in terms of portability, it ranks way lower than Java, but way higher than other languages, right? In fact, C, the C language, which is the grandpapa of C++, the reason it was created, like the main reason, Dennis Ritchie created C was for porting code. So Dennis Ritchie was a system programmer at that time, and his job was basically writing the operating system for the mainframes that were used in the company he was working on. All right. So imagine that's our job. Now we're talking in a time where hardware was far from being standardized, like today, where you have platform standards, right? Not like then. So basically, every time there was a new machine, the way it worked and the instruction set was different. So he would have to rewrite the whole operating system again, so that other people could use the system. Because remember, without an OS, you cannot use the computer. And so he basically got tired of this. He's like, okay, basically, in a way, it was laziness, but it was more optimizing his work. He's like, I don't want to have to write the operating system every time a new mainframe is got here. So his solution was to create a language, C, a language that was simple enough that it would be easier to write this kind of code, but also so that he could port the code. So what happened is that every time, whenever a new model would come, instead of having to rewrite all of the code, he would just have to write the compiler for that system, which is a way smaller program. That's all he had to do, and then he could move the whole code to the new system. Again, so in that case, a language, this particular feature here, he just sort of spurred the design of the whole language, one of the most important languages in the history of programming, being C. But nowadays, with the modern languages, C doesn't rank as portable as, say, for example, something like Java. The same person who mentioned C++ and Java also mentioned Python. Why is Python portable? If somebody else wants to answer, that's fine.
Because it's also an interpreted language.
Because it's the only interpreted language of those three. Java is not interpreted. Java is compiled, right?
Right.
So Java is compiled. C++ is compiled, but you're right. But Python is interpreted. So what that means is that as long as you have an interpreter for the target system, you can easily move the code. Similar to what happens with Java, but in the case of Java, it's not an interpreter. It's like fully compiled. It just compiles to bytecode and then it runs on a virtual machine. All right, so you have different degrees of portability. And of course, you pay some price with it. Because on the one hand, you have C++. It's not as portable as Java, but it's way faster because it runs directly on the metal, or almost directly on the metal. And then you have Java, which is way more portable because you can just move the binary, but it's not as fast as C++. And then you have Python, which is interpreted, so you can just move the text.
Wait, sorry. When you say as fast, you mean like on runtime or?
Runtime, yes.
Okay.
Yeah, I should say that. So the runtime of the program running for Java is not as, nowadays it's almost the same, very comparable, for certain applications at least. And then you have Python, where it's fully interpreted, so you don't even have to move binaries, you just move the text. But it's going to be way slower than Java, even because it is interpreted. So every line is interpreted at runtime. It's not compiled like Java. So again, the more you get, something you have to lose of something else. All right, and finally, the last two, we have cost, which is the cost of using a language. That's basically include cost of development, compilation, maintenance, execution, anything where you're going to incur a cost than you want to, even licensing the language, right? So some languages are proprietary, so you have to pay to use them. And so that's going to be a cost. If it's fully free, then you're probably going to choose that if you don't want to have to incur any. The problem is that you may choose a free language that nobody knows how to use. So now you have to pay in training your people to use them. So you basically have to see, what is it that's more convenient for you. And of course, another form of cost is execution time, whether it's fast enough or not. That could also translate in actual financial cost, or at least in performance. And then finally, expressivity, which is how flexible is the language in providing different ways to solving the same problem. Some languages are so constrained that they almost guide you in the way to solve problems, and that may be fine, and in some cases even desirable. But other times you want languages that are sort of allow free expression of the programmer, because it makes it more flexible to come up with quick solutions for problems, quick and concise. But the problem with those languages that are so expressive is that they might be a bit more error prone, because you have all of the different things that you can do. And also the code that they yield, what happens is that everybody is going to use it differently, because now there's like a million ways of solving problems, and that may cause issues of communication within a team or an organization. and also can make the code way harder to read. Obviously, expressivity is in tension with simplicity. Portability may be in tension with cost, and so on. Any questions up to this point?
How is expressivity different than like a high level of abstraction?
This is only has to do with this here only has to do with data abstractions. Whereas expressivity, it has to do with different ways of solving the same problem. For example, in Perl, there's like hundreds of solutions to a simple problem. So you can solve a problem in the conventional way, where you could say, let's say that you want to update all the elements of an array, and then you create a loop, and then you create, you sort of traverse, you update the elements, and that's one way to do it. And that's how you would have to do it in most languages. In Perl, you have one-liners, which they are basically this complex, regular expression-based sublanguage that allows you to specify that you want to traverse that array and add and change in a particular way every element in one line without loops. But the language is able to interpret that and turn it into that loop. And there's many other ways to do it as well. And so that language is expressive because it gives you the freedom. And the advantage of the one-liner is that it's concise, and oftentimes especially if you're a system programmer, you're writing a thing and then I want to update all of the lines in this particular file. And then you can just write a one-liner, boom, solve it real quick, and that's it. In Java, you would have to open the file and then load all of the lines and create an array and then traverse the array, and then in Perl, it's just one line. Does that make sense? So it has nothing to do with abstraction. It's providing different ways of solving different problems. Does that make sense?
Yeah.
Okay. Okay, we're gonna stop now because, well, we run out of time. I'm gonna post these slides immediately after, even though we're not done, so that you have them after class is over. And remember that we have a quiz on Monday of the stuff that we have talked about so far. Until then, have a good weekend. And I'll see you on Monday. Sounds good?
Thank you, Professor.